In this video, we're going to cover section 1.2 of chapter 1 and talk about how to find limits algebraically and the concept of continuity. So the objectives of this section are to develop and use the limit principles to calculate limits so we don't have to look at tables and graphs, and to determine whether a function is continuous at a point and on an interval. All right, so we're going to start off here just by going through our limit properties. So all the properties we're going to cover on the next several slides assume the following. The limit as x approaches a of f of x equals L, and the limit as x approaches a of g of x equals M. C is any constant. So the first property says that the limit of a constant is the constant. So the limit as x approaches a of the function c would just simply be c, because if the function f of x equals c, that means all y values are c no matter what. So it doesn't matter what x is, y would equal c at every single point. Property 2, the limit of a power function is the limit of the base raised to that power. Meaning, for positive integers n, the limit as x approaches a of f of x to the nth power is the same as taking the limit as x approaches a of f of x, then raising it to the power n. So in other words, you can bring the limit inside and evaluate and then raise to the power. So if the limit of this function was given in the beginning of this section to be L, so this inside would evaluate to the value of L, and then so that L raised to the nth power would be your result. Also works for fractional powers or roots. So the limit as x approaches a of the nth root of f of x, you can bring the limit inside and evaluate the limit first, then take the nth root of that result. So you end up getting the nth root of whatever this limit is. Okay, and that would assume that L is positive if n is even, because otherwise you get an imaginary number. Limit property number 3, the limit of a sum or difference is the sum or difference of the limits. So if you're adding or subtracting functions and taking the limit, this just says that you can take the limit separately, then add or subtract the results. You can distribute your limit through terms. The limit of a product is the product of your limits. So if you're multiplying functions, you can take the limit of each function separately and then multiply the results. The limit of a quotient is the quotient of the limits. You can take the limit of the top and the limit of the bottom, evaluate, and then divide the results, providing the denominator value is not 0. Otherwise, it would be undefined. So that is a restriction. And then the limit of a constant times a function is the constant times the limit. So the limit as x approaches a of a constant times a function means you can take the limit of the function and just multiply by the constant. So it's kind of like factoring the constant outside. All right, and then when you kind of put all those together, we can establish what we call theorem 2, which is limits of rational functions, and this also applies to polynomial functions. For any rational function, capital F, with a in the domain of f, this part is extremely important. If a, the value you're x approaching, has to be in the domain of your function, otherwise you cannot apply this theorem. The limit as x approaches a of capital F of x is simply f of a. So in other words, you can evaluate by direct substitution. So you can plug in a into the function and get the value without having to go through all of your properties. So a rational function means it's a function that can be written as a quotient of polynomials. So it's either just a polynomial by itself, or it's the quotient or division of two polynomials. So those are the types of functions that this would apply to. All right, so use the limit properties to find. So the directions say to use limit properties, but we're going to actually use the theorem because it's a little bit more efficient. Limit as x approaches 4 of x squared minus 3x plus 7. So we could apply each limit property to each term of this function to evaluate. However, it's much more efficient to use theorem 2. Since this is a polynomial, meaning that you have positive integer powers of x's here, you don't have any roots or weird exponents or anything, we can evaluate the limit by direct substitution. So the limit as x approaches 4 of this function is simply found by plugging a 4 in for all the x's. So 4 squared minus 3 times 4 plus 7. 16 minus 12 plus 7 is 11. And this works because 4 is in the domain of our function, and that function is a polynomial or rational function. Remember, that theorem only applies to those types. Okay, and the value we're approaching has to be in the domain. In other words, it can't cause your function to be undefined. That is equivalent to showing each step of applying each of those properties that were listed. So later in another example, it walks you through all of the property evaluation steps, but the end result is simply direct substitution. All right, find the limit as x approaches 0 of the square root of x squared minus 3x plus 2. So this time we have that root property that we talked about. You can bring the limit inside, and once you bring it inside, it's just like our last example, so you could do a direct substitution here as well. So the theorem on limits of rational functions and limit property number 2 tells us that we can evaluate by substitution. So bringing in the limit inside, then plugging in a 0 for all the x's. 0 squared minus 3 times 0 plus 2 ends up giving you a 2 underneath here. So that 2 underneath your square root, or the square root of 2. All right, so here we're going to try a few more examples. Finding the limit as x approaches 1 of 2x cubed plus 3x squared minus 6. Limit as x approaches 4, 2x squared plus 5x minus 1 over 3x minus 2. And the limit as x approaches 2 of the square root of 1 plus 3x squared. So all of these can be done utilizing our rational theorem and properties that we have talked about. Direct substitution will apply here because 1 is in the domain. Direct substitution will apply to the rational, the quotient of polynomials, because 4 is in the domain. In other words, 3 times 4 minus 2, that doesn't give me a 0 on the bottom. And then just like the last one, we can bring the limit inside and do direct substitution on part C as well. All right, so here they're going to walk you through the steps as if you were using properties instead of the shortcut, just to kind of show why the answers are equivalent. All right, so just before we get through all of this, if I were to plug a 1 in here for x, I would get 2 plus 3 minus 6, which is negative 1. That should be my answer when I'm finished, okay? All right, so they start off by saying we know that the limit as x approaches 1 of just the function x is 1. And you can plug in a 1 there. Okay, so if we start with that fact, then the limit as x approaches 1 of x cubed, which is this term here, by our product property, we could do split up x cubed as x times x times x. So we know all these limits are all 1, so 1 times 1 times 1 is 1. So then if I wanted to multiply that by a 2, we have that property that says you have a constant multiple. You can pull that 2 out in front, right, times your x times x times x, so you get 2 times the 1 from here, so that's a 2. X squared would be just x times x, so if that limit is 1, that's 1 times 1, which is 1. So then multiplying that by a 3 gives me 3 times 1, which is 3. And then the last term is a constant, 6, and the limit as x approaches 1 of any constant is just the constant 6. And they're citing all of those rules that we looked at the beginning. So then if you combine all those together, it's simply the equivalent of just substituting in 1, right? So that's why in that first example I went through just the shortcut, because that's probably how you're going to want to be doing these in the homework. Otherwise it's going to take a really long time and a bunch of steps that are really not necessary if you apply your theorem. All right, number 2, we know that so they do the exact same thing here. I'm going to kind of go through these pretty quickly. They go through, what they know about just x, apply it to the 2x squared, then apply it to the 5x term, then apply it to the constant term, and then put all that together to get your numerator basically to be 51. Notice if you plug in a 4 here, 2 times 16 plus 4 times 5 minus 1 should be 51. All right, then the bottom, they do the same thing. 3 times the x would just be 3 times that limit, or 4, then your limit of the constant is 2, and then when you combine, it's the equivalent of plugging 4 into the bottom, which would give me 10. And then just simply dividing. So they basically use the property of bringing the limit to the top and bottom, then going through all the property steps on top and bottom, getting these results, and then evaluating. Okay, that's really unnecessary because you can simply plug a 4 in for all your x's and get the same thing. All right, in part C, they do it, again, by properties. So the constant term has a limit of 1, then the polynomial term using the product property and the constant multiple property, and then combining those together is just substitution. So plugging in a 2 here gives me 2 squared is 4 times 3 is 12 plus 1 is 13. And since you bring it inside under the square root, your answer should be the square root of 13. So I would suggest just knowing the more efficient method of direct substitution when it's possible. All right, here we want to find the limit as x approaches negative 3 of x squared minus 9 over x plus 3. All right, we have an issue here because yes, this is a rational function, but negative 3 is not in the domain. Meaning if I plug negative 3 in for x, on the bottom I get a 0. So that means it's not part of the domain. So the theorem of rational functions does not immediately apply because negative 3 is not in the domain of our function. So we have to be careful here. All right, however, this function will simplify. Okay? And once I simplify it, sometimes then you're able to evaluate, other times you're not. In this case, we will be able to evaluate after we simplify. All right, so simplification here means I should notice I can factor the numerator into x plus 3 and x minus 3. Notice then we have a common factor on top and bottom. This x plus 3 factor is common with the bottom term, x plus 3, and they can cancel. So we keep our limit in front here. The limit as x approaches negative 3 then becomes just equivalent to taking it of just what's left over, x minus 3. So this is a polynomial function, meaning you can just do direct substitution. So I plug negative 3 in for the x and evaluate, and this limit is equal to negative 6. So remember, even though this function is undefined at negative 3, it still has a limit as I approach negative 3 to equal the number negative 6. So the limit exists as x approaches negative 3, but the actual point does not. So there would be a hole in the graph if you were to look at the graph of this function. All right, so let's try this one. This one says find the limit as x approaches infinity. So there's a process, since we're not plugging in a number this time, there's no direct substitution because you can't plug in infinity. So our process here when we're approaching infinity, first divide the numerator and the denominator by the highest power of x in the denominator. So if I look at my denominator here, the highest power of x is x squared. So we're going to divide every term on top and every term on bottom by x squared. All right, so there's our function. If I divide x squared divided by x squared is where they get the 1. 4x divided by x squared simplifies to 4 over x. And then minus 5 divided by x squared is just 5 over x squared. Same thing on the bottom. 2x squared divided by x squared is 2. Plus x divided by x squared is 1 over x, plus 1 divided by x squared. So that's where this comes from, dividing everything top and bottom by the highest power of x from the denominator. All right, then with your limit properties, you take the limit into the top and the limit into the bottom and then distribute it through each term. So this becomes the limit as x approaches infinity of 1. Plus the limit as x approaches infinity of the 4 over x minus the limit as x approaches infinity of 5 over x squared. And on the bottom, the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 1 over x squared. All right, and then from limit properties, limit as x approaches infinity of 1, no matter what you're approaching, if the function is a constant, it's just 1. All right, here, notice x is getting very big. It's approaching infinity, and it's in the denominator, but the numerator is staying constant. Anytime you have that the denominator has a higher power of x than the numerator does, then if you're taking the limit as x approaches infinity, that's going to approach 0. The larger the denominator gets, the smaller the value of the fraction gets. So that applies here, makes that go to 0. It also applies here because the bottom's getting really big with the top staying constant. That goes to 0. So that's where these zeros come from. On the bottom, That's a constant, so our limit no matter what is 2. Again, the bottom is getting big, but the top's not changing at all, so that's going to be a 0. And then same thing here. The bottom's getting really big, the top is not changing, so that's going to go to 0. So you cancel those out as being evaluated at 0 because you're taking the limit as x approaches infinity, and there's an x on the bottom but not on the top. And then that simplifies to 1/2. So this limit of this function would equal 1/2. So let's try another one like this. So to find the limit as x approaches infinity of this function, notice you look at, since you're approaching infinity, you look for the highest power of x in your denominator, which is x cubed. So we're going to divide top and bottom, every term on top and every term on bottom, by x cubed. So divide numerator and denominator by the highest power of x of the denominator, being x to the 3rd. So there's our function. When I divide everything on top by x cubed, it simplifies to these terms. And when I divide everything on bottom by x cubed, we would simplify to this. Then you use your properties and you bring your limit into the top and the bottom and distribute it through each term like we did before. So you're taking the limit as x approaches infinity of each of those separate terms. And then everything that has a denominator that contains x and a numerator that doesn't goes to 0. So it goes to 0, goes to 0, 0, 0, and 0. Right? All these things become 0 because the bottoms are getting really big, but the tops are not changing. And otherwise, your constant of 2 on the top is left, and the constant of 3 on the bottom is left. So we end up getting 2/3. All right, so our next part of this section is talking about the concept of continuity. A function is continuous at a number a if, and there are 3 conditions you have to check for continuity. Number 1, the function evaluated at a exists. Okay, in other words, there's a value of the function at the x value of a. So if f of a is undefined, it's automatically not continuous. The limit as x approaches a of f of x exists. So it has to have a limit. Okay, if it's a piecewise function, we have to evaluate by the left versus the right. We have to check that so that those 2 values would have to match. So you have to have a limit. And the limit as x approaches a of f of x that exists here and the value f of a that exists here must equal each other. So you first check for existence of these 2 things, and then you check their values and make sure that they are the same. So a function is continuous over an entire interval between 2 numbers c and d if it's continuous at every single point. So these are the checklist criteria for checking a single value a. All right, is the function f given by f of x equals x squared minus 5 continuous at 3? Why or why not? So we're going to go through our checklist. All right, number 1, does f of 3 exist? So f of 3 would be 3 squared minus 5, 9 minus 5 are 4. So yes, it exists. Does the limit as x approach 3 exist? So by your theorem of rational functions, limit as x approaches 3 of x squared minus 5, we can do by substitution. 3 squared minus 5, 4. And since we got the same value for the value of the function that we did for the limit, then yes, it is continuous at 3. All right, this next example is piecewise. So piecewise are handled a little bit differently. We still have our 3 conditions of our checklist, but to evaluate the function versus the limit, we got to think about how our function is defined. So is this piecewise function continuous at -2? Why or why not? All right, so is it defined? Does it have a value at -2? So here we have to look and see, okay, for x's that are strictly less than -2, we apply this piece, but for x's that are greater than or equal to -2, we would apply this one. So the equal to -2, right, is here. So we would plug into this piece of our function. So -2 minus 1 is -3. So yes, it has a value at -2. All right, then we're going to look at the limit. On a piecewise function, when you're evaluating the limit at the breaking point where they switch definitions, right? That's the value of x we're approaching. We have to look at left and right-sided limits, right? Because when I'm viewing my left limit, I have to apply to this function versus my right limit applies here. So we start with the limit as x approaches -2 from the left of our function. So if my coming from the left means I'm coming from values that are smaller than -2. So that's where this would apply. X's would be less than -2. So all those apply to this equation. That is a polynomial, so we can plug in the value that we're approaching. So 1/2 times -2 plus 3 is -1 plus 3, or 2. So that's using limit properties instead of our table method. We just apply those limit properties to that first piece. So the limit as x approaches -2 from the left is 2, because that's what we get when we plug in -2 into the top piece. All right, limit as x approaches -2 from the right means you plug it into the bottom piece. Okay, remember the bottom piece is x minus 1. From the right side, x's are bigger than -2, so that's why this one applies in that case. So -2 minus 1 is -3. So since the limit as x approaches 2 from the left and the limit as x approaches 2 from the right were not the same, we got different results, the limit as x approaches -2 in general does not exist. So that's the second part of the checklist. Does the limit exist? And since it doesn't exist, we stop and say the function is not continuous at -2. All right, so let's try this one. Is g continuous at 2? So again, a piecewise function where we have the breaking point at 2 where we're looking for continuity. All right, so check to see if it exists. Does the function have a value at 2? So g of 2 means you find the one where the equal sign is, which is down here. So you plug it in here. 2 times 2 plus 1, 5. To find the limit, we look at left and right again because it's piecewise. So from the left, values less than 2 means we plug into here. 3 times 2 minus 5, 6 minus 5, or 1. Limit from the right means I'm bigger than 2, plug into here. So 2 times 2 plus 1, 5. Those are not the same. So since the left limit and the right limit are not the same, the limit as x approaches 2 does not exist, and therefore this function cannot be continuous at 2. All right, here's another piecewise function. H of x equals x squared minus 9 over x minus 3 for any value of x not equal to 3, and then the function h of x equals 7 if x is equal to 3. So we want to know, is this function continuous at 3? All right, so we can see here that at 3 the value is 7. So h of 3 would just equal 7. Okay, well, they don't do that till the second step here, but we can see that real quick. But we do need to calculate our limit. The limit, this is what has to happen. The limit as x approaches 3 of the function h of x needs to be the same as h of 3. So they start by finding the limit. Now this is a piecewise, but notice we don't have to do a left and a right because for the way it's defined. For any value not 3, meaning from the left, and so numbers on the left of 3 and numbers on the right of 3, both get applied to the same piece, this piece right here. Right? As long as we're not 3, so if you're on the left of 3 or the right of 3, doesn't matter, this is how the function is defined. The limit as x approaches 3 of h of x, left or right, so there's no direction specified, is simply x squared minus 9 over x minus 3. The top, notice I can't just simply substitute here because 3 is not in the domain because it gives me a 0 on the bottom. But again, I can factor the top. That allows me to simplify and cancel out these x minus 3's, leaving just this. The limit as x approaches 3 of x plus 3. Then I can substitute once I've simplified and get 6. So the limit as x approaches 3 is equal to 6. Whoops. Sorry. Hold on a second here. Move that back to where we were. Right, okay. 1 second here, guys. Hold on. I got this all. Trying to get back to where we left off, where it messed up on me here. Hang on. All right, so here we were. So we got 6 for that answer. All right, so the limit as x approaches 3 of h of x equals 6. However, h of 3 is 7, right? H of x is equal to 7 if x were equal to 3. So that means at 3, the value is 7. So we had a limit existing, we had a function value existing, but they're not the same number. So this is another way it can be not continuous. So it's not continuous at 3 for that reason. All right, so our summary of this section. For a rational function for which a is in the domain and the limit, then the limit as x approaches a can be found by direct substitution. If you can do direct substitution and it leads to an indeterminate form 0 over 0, meaning you're undefined, the limit may still exist, but you have to simplify algebraically or use a table or a graph. All right, informally, a function is continuous if its graph can be sketched without lifting the pencil, right? But that's basically what those 3 criteria of our checklist show us. So formally, to check if a function is continuous at a, the function has to have a value at a, the limit as x approaches a has to exist, and then the function value and the limit have to be the same. So it's summarized as this, that your limit as you approach a has to equal the value f of a. If any part of the continuity definition fails, if any of those 3 conditions are not satisfied, the function is discontinuous at a. And that is the end of section 1.2.